Thank you, Peter, for the introductions. Thank you, everyone, for joining my presentation today. My name is Jordan, and I kind of put my name in the reversed East Asian order. I hope that doesn't cause too much confusion. So Jordan is my first name, Shen is my last name. And I graduated in 2019 from the University of Hong Kong with a bachelor's degree in computer science. And during that time, I have had research internships in SenseTime and Tencent, two Chinese companies. That's how my deep learning journey started. And after graduation, I joined Google's AR residency program, and I kind of stayed there for about almost 2 years. And across the three companies, I've been focusing on a single field of research, which is self-attention for computer vision. And which will also be the topic that we're discussing today. And I'm currently kind of in the middle of a job change. In a few weeks, I will be joining Pony.ai to work on their perception system. Yeah, so that's basically about me. And let's dive into the topic. Oops. Okay, yeah, let's dive into the topic. So today's presentation, as the title suggests, is about efficient attention for computer vision. And it is divided into 3 sections, which corresponds to my series of 3 works along this direction. The first one is efficient attention, which basically solves the problem that the vanilla version of self-attention has quadratic computational and memory complexities, which is not really affordable, especially for computer vision tasks. So my efficient attention was one of the methods to bring down the complexity to linear so that it is much more affordable. You can apply it on high resolution inputs, you can apply it on video inputs, or you can use it extensively as much as you want, because being down to linear complexity basically means that this is as expensive as a single convolutional layer. And the second part is about global context module, which is basically a streaming version of efficient attention that is specifically designed for videos. And back then we were working on a specific task called video object segmentation, and we'll get more deeply into it in that section. And the final one is global self-attention networks, which is the work that I did at Google. And it is basically about, instead of in the previous works, using attention as an auxiliary module that helps a mostly convolutional network, and to help convolution on fronts that attention does better, does way better than convolution, like in modeling long-range relations, etc. We instead want to make a fully attentional or mostly attentional network that uses the attention mechanism as a backbone. And if it still has any convolution in it, that will be the auxiliary part into it. And we'll see this series of work that I think basically started back in 2018 and digged quite deeply into this field. You probably should ask, like, what is the motivation behind all this pursuit? Although we can name many advantages of the attention mechanism, I think the 2 most fundamental properties that makes it unique is that number one, it's very efficient at establishing long-range relations. For example, if you use traditional methods, let's say you use convolution, you would be looking at a 3x3 or maybe 7x7 patch of an image at a time. And in order to get a global view of the image, you either have to stack many layers of convolution to gradually expand the field of view, or you have to use a large number of pooling to really decrease the resolution so that each of the remaining pixels sees the entire image. Similarly, if you use RNN, if you use the recurrence mechanism, then you are then along the temporal axis, you are modeling it step by step. So if you want to see 10 time steps before, you have to go 10 steps or 10 hops until you actually see that information. Which is in a stark contrast with attention, which establishes global connections in just a single pass. So if you have a single attention module or attention layer in your model, that layer can just by itself make every pixel see every other pixel, at least theoretically. Another unique property about attention is that its connections adapt to different input data. So for CNNs or RNNs, what happens is that at training time, the connection strength between different neurons are being tuned. But once training is finished, if the model is deployed or is in inference mode, the connection strength between any pair of neurons is already fixed. It doesn't change at all, no matter what kind of data what data you put if you do it. But for attentional models, the connection strength between neurons in adjacent layers is decided dynamically, so that when the input data is different, the connection patterns will also be different, and that seems to be a more flexible way to make these connections, so that an attentional network with the same amount of parameters tends to appear to have a higher capacity than a similarly sized ConvNet. And I think these are two really important properties that makes attention very unique and attractive. And I think it's very suitable at the current stage of deep learning's development. So before, by the way, I think Peter already said that, but I would like to repeat. So if you have questions, you can just interrupt me at any time. You can just interrupt me vocally, or you can use the raise hand feature or type in the chat or whatever method. Just interrupt me and we'll answer your question. Yeah, so before diving into the details of my works, let's have a review of the dot product attention mechanism, which is the vanilla version of attention that all of my works and the follow-up and other people's follow-up attention works are building upon. So essentially, let me see where is the laser pointer. Yeah, so essentially, dot product attention is a naive implementation of the idea that the more similar you are, or the more related you are, the more connected you should be. So the way to measure how similar or how related two points or two pixels are is that you generate a query vector and a key vector for each pixel, and you compute the dot product between each pair of query and keys, and so that the dot product value will be measuring the relatedness between point A and point B if you are multiplying QA to KB. And to do that, you can basically just arrange these query and key vectors into two matrices and multiply them to each other, and you will have a huge n by n matrix, n by similarity matrix, or I think it would be more accurate to describe it as a relatedness matrix. This is intended to be asymmetrical. And to get those query and key vectors, we usually just simply use a pointwise layer, or also known as linear layer, to generate the queries and keys. And once you have these similarity scores between pairs of pixels, after appropriate normalization, they will be the connection strength between that pair of pixels, and that will be the same for all n squared pairs. And we will use these connection strengths, we will use these weights to aggregate or weightedly average the value vectors, which also comes from the input matrix via usually a linear layer. And that would give you the output, that will give you the output of this attention module, which will have the same dimensionality as the values, but we would usually just make it the same size as the input so that we can apply things like residue connection and other things that are typical in modern neural networks. This is very effective, and as I just said, is very effective at establishing long-range relations because each pair of pixels is directly connected. So with a single module, each pixel here already has the information from every pixel in the input. But the downside is that, as you can see, there is a huge n by n matrix, which causes the quadratic complexity. And because this mechanism originates from the NLP field, back then people were working on sentences or paragraphs, which are maybe up to 20 or 100 words, so that if n is 100, the quadratic complexity was okay. But once you move this into computer vision, into the pixel domain, we would have pictures of millions of pixels. Even though in computer vision we usually work on lower resolution images, the quadratic complexity is still too much, especially in the early layers. So that is why that is what motivated me to venture into efficient attention, which was a work that tackled the problem of this quadratic complexity. So if we take another look at this this module structure figure, we will see that the only thing that causes a problem is the similarity matrix. And the reason that it's quadratic is because we are computing one similarity score for each pair of pixels. And that is probably redundant. So back then, my thought was that instead of is there a way to reach at the same destination or a very similar destination without generating this huge n by n matrix? And my thought process, the thought process that I went through was more complicated than this, but eventually what I discovered was that this actually is, if you look at it just from a purely linear algebra perspective, and for brief moment ignore all the non-linearities, what you can see is that this is essentially just two consecutive matrix multiplications. So a very simple way to make it more efficient is just to switch the multiplication order. After that, you will no longer have this n by n huge matrix, and you will have a much more compact dk by dv matrix. Of course, this isn't saving you anything if d and n are all numbers that are similarly large. But in reality, usually the number of pixels would be much larger than the number of channels that you have in a computer vision network in most, I would say in most layers. And in addition to that, these two numbers are what you can control when you design the network. And instead, the number of pixels in a picture is already decided when you get that picture. It's decided by the data, not by the network designer. So this is basically the core idea of efficient attention, how to bring down the computational and memory complexity from quadratic to linear. And after that, I will briefly talk about a new way to interpret attention that this new formulation brings, which is also how I reached the final form of efficient attention. So But basically, my initial thought was that it was probably redundant to have one attention map that covers the entire picture for each pixel, because many pixels are probably quite similar to each other. For example, if you look at this picture of a plane, there are a ton of light blue pixels in this area. They essentially don't mean anything different from each other. They are just like one pixel in this region of the blue sky. And because they are semantically not meaningfully different, and also self-attention is trying to decide the connection strength based on the semantics of different pixels. We should reasonably expect that they would have a similar pattern of attention. To capture this redundancy, my thought was that we instead of having a separate attention map for each pixel, we could have a set of shared global attention maps that serve as the basis attention maps for every pixel. For example, we have a set of 32 basis maps or 64, whichever number you decide for. And each pixel, instead of generating a full attention map for itself, it just generates 32 or 64 coefficients. And we would use these coefficients to combine those basis maps to form the attention map for that pixel. And but if you actually recombines those basis maps and actually generates that the attention map for that pixel, you would end up having one attention map for each pixel, which goes back to quadratic complexity. So what you instead should do during actual computation is that you should first apply those basis attention maps onto the values and already aggregate them into vectors. So each basis map would generate a single basis vector from the input from the values. And then you only need at each pixel, you only need to recombine those vectors using the coefficients, so that the entire process is very efficient. And this actually very nicely corresponds to the mathematical form, because what happens is that you can directly reinterpret this K matrix as the basis attention maps. So instead of viewing them as n vectors, each corresponding to a pixel down here, you could view them as dk single channel feature maps, and each one of them is a basis attention map. And you can use, and to aggregate the values means to apply it to multiply it onto V and generate this very compact dk by dv context matrix, where you can basically see them still as dk vectors, each of length dv, where each of the vectors is summarized from using one of these basis maps. And then you can reinterpret the queries instead of being queries as the coefficients that is generated for each pixel. And you can multiply this again to the context matrix and get the output. And so this new interpretation, and because these two modules are mathematically equivalent, except for the nonlinearity, the result is that this new interpretation basically also applies to the old way of doing attention. So, so these are two different ways of implementing the same mathematical transformation, and the traditional way of interpretation and the new way of interpretation applies to both of these modules. And let me still have a slide for, okay, I don't have. So let me spend a bit of time explaining how to deal with nonlinearity. There are basically two ways to deal with it. One is just not to have nonlinearity, so that it does not become a problem. And we have experiments both from our experiments and also from the previous non-local neural network work that shows just having a linear normalization, which basically means dividing this by a constant, doesn't really hurt performance versus other ways of normalization, for example, softmax. So that is one way to solve it. Another way is if you insist on having softmax, we can, instead of having a single softmax, a single, I think it's row-wise softmax on this matrix, we can factorize that softmax into two separate softmaxes on Q and K, and the Q one would be column-wise, the K one would be row-wise, so that the end result is that if you still multiply these two back together to generate that S, this S would be slightly different from the S on the left, but it will share, but it still has the critical property with that each row sums up to 1, which and forms a probability distribution, which is kind of, I guess, a central property for attention. Yeah, so next time I'll show some experimental results. What can I see is, I think this was done, these experiments were done on the MS COCO dataset, and we had a mask RCNN backbone network, and we were inserting efficient attention or the traditional non-local module, which implements dot product attention into different layers. And we can see is that if you insert an EA module and a non-local module at the same layer, they basically always have the same performance. But if you insert non-local modules into the higher resolution parts of the network, it will go out of memory. And also the memory and the computational cost, as you can see, is way higher if you use non-local module, but the result is almost always the same. If you instead control the amount of memory you use and find the best model that fits into memory, you can see that by being more efficient, you can fit more EA modules on a fixed amount of graphic memory, and you will be able to reach better performance under the same constraint. We have other results, stereo depth estimation on the scene flow dataset, and also temporal action localization on Thalamus 14 dataset. These were not done really extensively, and was basically just to show that our module did not overfit to the task of detection and segmentation. It's a general method that applies wherever traditional self-attention applies. And next up, next up, I will be talking about the global context module, which, as I said, is a very simple extension of the efficient attention module, and it basically extends it into streaming video data. But the work was done on a specific task, which is called semi-supervised video object segmentation. And this task is actually quite similar to tracking. So your input data would be a sequence of video, and on the first frame you will have a. Why is it going just by itself? On the first frame you would have a finely annotated object, and your task is to find it on each of the following frames and segment it out. And traditionally, there are two schools of approaches to this problem. The first one is online learning, which essentially trains a meta segmenter. And when you have a new video sequence, you apply a lot of data augmentation to the first frame where you have the label, and use that, and use the small data set that you generate by augmenting the first frame to fine-tune the meta segmenter to build an object-specific segmentation model that specifically looks for that object. And after finishing training, you apply that model on the remaining frames and get results. This type of method tend to have pretty accurate results, but because at inference time, which you should be doing inference, but if you do online learning, I actually have to do some training. What happens is that this type of method is usually really slow. If you want to go faster, you will be moving to the offline learning school to solve this problem. And within offline learning methods, you can further divide them into 3 subcategories. The first one is template matching methods, which essentially treats the first frame as a template. And in each of the following frames, you try to look for pixels that match pixels in the template. This method is very prone to appearance change because if you have a slightly longer video, then the object that you want to track will change in appearance over time. For example, I think the camel here on the first frame is showing its side to us, but in the last frame it's already showing its rear, and this, if you look at it naively, looks quite different from this. So if you only use the first frame as a template, you would suffer a lot from when the object changes appearance, and you might just lose track of part of the object or even the entire object. Another subcategory is mask propagation methods, which basically directly targets the appearance change problem. It's basically saying that instead of using the first frame as the reference, let's use the last frame. Let's use the immediately previous frame. That frame is the closest to the current frame that we're trying to process, so that the appearance change should be minimal. And although that is true, but then you have another problem, which is that you don't have any labels for any of the frames except the first one. So from the second frame onwards, you are not propagating a ground truth segmentation mask. You're rather propagating your own prediction to the next frame. And as we all know, machine learning models are never perfect. So if you make a mistake on one of the frames, that will be carried on to the next frame and will be basically stay there permanently. And as you go through a video, the errors will start to accumulate. And when you have gone far enough, your segmentation results will be really messy. And another problem that will cause another thing that will cause big problem to mass propagation is occlusion. Because when part of the object is occluded, you would not track that part on this frame. But if a few frames later, that part of the object reappears in the view, if you just do naive mass propagation, you would lose that part permanently. To try to mitigate these problems, there are, of course, hybrid methods that tries to combine these two methods somehow and try to find a balance in the middle. But the most successful one in the hybrid methods, and also the most successful one in the entire offline learning school, at least at the time of our work, was called the space-time memory module. It was basically saying that instead of picking whether to use the first frame or the previous frame or some frame in the middle or some combination of that, why not just use all of them? That would, if you use all of them, you would benefit from any information that any of the frames can provide you. But because all of them means different number of frames and different, we are processing different frames, you need a flexible module that can connect to past memory that changes in size. And the space-time memory module basically just chose a dot product attention mechanism to do this job. And this is the overview of their network structure. Essentially, so at each frame, you have an encoder that encodes the frame not into a single feature map, but into a pair of key and values. For the current frame under processing, you have a slightly different. You have a different encoder called the query encoder, and the essential difference is that the query encoder is a normal encoder that takes a 3-channel input, while a memory encoder takes in a 4-channel input, where the 4th channel is the mask. And we have all these keys and values. You can use the query keys to query all the memory keys and get an indexing, and use the indexing to read the value, to read the memory values, to get the memory reading, and finally concatenate the query values onto memory readings to get the final representation that will fed into the decoder and get the final segmentation results.
I think have a question. Sorry. Yeah, are all the frames weighted the same, or do you take like a higher weight for a closer frame or something like that?
The weight will only depend on the matching results between the memory keys and query keys. So we don't artificially introduce different weights. Or I mean, they didn't artificially introduce different weights. It's not my word.
Okay.
Yeah. Yeah. Or if you're asking a question, if you are willing, you can probably also introduce yourself a bit, like what are doing and your name, so that we can know more about each other through this presentation. Yeah. So yeah, as I said, this is basically just a vanilla version. They're basically just using the vanilla version of attention, not introducing any artificial weights or whatever. But they did kind of abuse the terminologies a bit. If they closely follow the dot product attention terminologies, these would be queries instead of keys. These are the actual keys. These are actual values. This has nothing to do with attention. This is basically just a separate feature map that will be concatenated to the readout from the attention module. But they decided to name it this way. Maybe it looks nicer on their work. Yeah.
I'm sorry if I'm repeating something we discussed. Maybe I missed it. The indexing part, what does it do exactly?
This indexing is basically exactly the same as the score matrix here.
Okay.
So, so each of the keys and values are not a single vector. They are a feature map. So let's say your last layer output 7x7 feature map. That will be 7x7 by C, where C is the number of channels. And this key query matching part is not between frames, but it's between individual pixels on the feature maps. So we'll basically have if all these are 7x7, we'll have a 49 by 49n matrix, where 49 corresponds to the 7x7 pixels here, and the 49n corresponds to the n sets of 7x7 pixels here, and each pair of them will have a similarity value. Cool.
Thank you.
Yeah. So
can I ask a question? So when you say frame, is it video frame or it's pair? It's video frame plus if for the first frame is like segmentation mask, and for the next one is predicted mask, or its frame is like only video frames? Is it pair?
Yeah, I didn't make it very clear in this figure. So frame T is just a video because we haven't processed it. Frame 0 through frame T minus 1, they are 4-channel frames where the 4th channel is a segmentation mask. And for frame 0, the 4th channel comes directly from the annotation because we have the annotation. Frame 1 through T minus 1, that 4th channel comes from the prediction that the network made when it was processing the frame. Is that clear enough?
Yeah, I think.
Yeah, cool. Thank you for the question. Yeah. So basically what I saw from this is that this is essentially using the dot prioritization mechanism. So we could just apply the efficient attention trick onto it. And when applied here, the specific form would be, because in efficient attention, we would multiply keys to values first. So we can just directly do this right here. So we no longer need to store keys and values. We can just store what I called a frame context matrix. And if you recall from the previous figure, this thing has a fixed size. It's always dk by dv. It has nothing to do with the resolution or whatever. And after having frame context here, you can just average them into a global context. And when you are in the memory readout step, would essentially still be the same. It would multiply keys onto the global context, but to better describe what's actually happening, I chose to call this the context distribution step. But this essentially is just to still multiply these together, and then concatenate the values as we do.
The global context is just plain averaging. There's nothing that, for example, looks at the later frames and saying these are more value or more significance in any way. No query being multiplied there.
No, we are not doing any of these because I think essentially this you can understand it through the fact that this is basically modular normalization. This is mathematically equivalent with this. And just as here, we don't introduce any artificial weights. We just let the keys match and see which one is more important. Because I think the later frames would naturally have more weight because they look more similar to this frame. And that's essentially, so we essentially don't try to artificially introduce any directions at which things are more important. We try to let the network learn what is the best way to represent information and attribute your attention.
So maybe I'm missing something, because here you don't multiply the keys before the averaging, while in the previous slide there is the multiplication. So that's the part I'm missing, maybe.
Yeah, but mathematically they are just the same, because the
Hello. Hello.
I can hear you, Peter, but I can't hear the presentation as well.
Yeah. Well, let's see. Wow. Let me see. Maybe he sent me something via email. Okay, let me see. Oh, completely gone.
yeah, hi, I'm back. Sorry about
okay. that. But your
Yeah,
face changed the box.
I think it's just like it was just my VPN disconnected, because I'm presenting from Beijing.
By the way, what's this thing with the VPN there? You can't connect with Zoom, or how does it, what?
I can't connect to Zoom without VPN, but I was like also using Google and other things, so I just had my VPN on.
Wow.
Yeah, so I disconnect from a VPN just to have more stable connection.
In the end of the call of the talk, I would love to hear a bit more about how you're usually using internet from Beijing, because we don't have that going. So
yeah,
out of
sure.
curiosity. Yeah.
Sure. We can mix that into Q&A part if we have time. Yeah, but I'm sorry I forgot what we were talking about before I disconnected.
So in this slide you're showing now, the keys are multiplied. Well, I think the keys was the queries, basically, if you look at real attention terminology. So the queries are multiplied by what I think it should be the values before the indexing part, before the averaging part is happening, if I understood it right. But
Yes.
in the next slide, here, that's not happening. So first we have averaging, and then we have the multiplication, and you're saying mathematically it's equivalent. Maybe I'm missing something. That's the thing.
It is. Yeah. Let me see how to describe it more. I probably should make one more slide just on that, because yeah, I see that I wasn't explaining it very well here. Oops, where is my laser pointer? Yeah, so yeah, we're doing this multiplication here, and we have a 49 by 49 n matrix here, and then we multiply them onto the n values.
Understood.
And this step,
yeah, because of the n.
Yeah, this step is essentially doing averaging. So we just do the averaging here. It's the same.
I think what
Cool.
maybe,
yeah, but thank you for the question. I probably should add one more slide here.
You don't really have to. Maybe if you just add dimensions on the outputs and inputs of stuff, that's enough. Like if I knew there was by n there and the average is on n,
sure.
it's fine. Yeah.
Sure.
Thanks.
Cool. So after that, this is an overview of the complexity comparison between the STM module and our GC module. As you can see, we are like so much more efficient. And empirically, the result is that and GenF mean is the typical metric that we use to measure how good a video object segmenter is. We are contrasting that with the FPS number, and what we can see is that we are clearly at the top right corner. We were clearly at the top right corner. I think there are probably some methods that surpass that now. If you if you need more context, the GenF mean is, as the name suggests, the average value between the J metric and the F metric. The J metric is basically the IOU, while the F metric is boundary accuracy. And we have some visualization, and I guess you can see this is tracking things pretty nicely. The camel was tracked almost perfectly, and I think it's a dog. Yeah, this dog just really shows the power of utilizing all past frames, because you can see it has went through a lot of occlusions, but the model was able to recover the missing parts in later frames. And yeah, I guess that's essentially it. But it's not perfect though, because as you can see in this one, because the motorcycle has some very delicate structures, and the model was not very good at getting it all right. Cool. So after that, we will move on to the final section of this presentation about the global self-attention networks, or GSA-Nets. As I introduced in the very first part of the presentation, the entire mission of GSA-Net is to is to achieve fully attentional modeling, so that we can use attention as the centerpiece for computer vision modeling instead of having it assist a mostly convolutional network. And we have three main points that really motivated us to do this. The first one is that in convolutional networks, there is basically an inevitable semantic resolution trade-off in all modern networks. What happens is that in the early layers, for example, we have a ResNet. In the very first layers, the resolution is pretty high, but it was still building up some very low-level semantics like edges, basic shapes, and colors. It was only in the later layers that it starts to build more, higher semantics. For example, it will start to recognize eyes, people, cars, things like that. But those parts have already gone through a lot of downsampling and has very low resolution. And essentially, a lot of works in computer vision are trying to combat with this semantic resolution trade-off. For example, we have feature pyramid networks, which in other than the typical main pyramid, add another pyramid that goes backward, and so that we can potentially make high semantics, high resolution feature maps, and which would be very useful for tasks like detection and segmentation and stereo vision, things like that. Yeah, there are other things like UNet, HRNet, or SPINet, which instead of going steadily from high resolution to low resolution, randomly sets the order of resolutions. You can go from high resolution to low resolution to mid resolution, and high resolution again, things like this. There are many methods that trying to combat this trade-off. And our hope, at least back then, was that if we can make fully attentional modeling work, then because we would no longer rely on downsampling to expand our field of view, we could we potentially could have just a cylinder structure network that has the same resolution from the beginning to the end, and it would so that in the later layers we would natively produce feature maps that both has high-level semantics and are high resolution. And a second thing is that attentional modeling looks very suitable for large-scale representation learning that has been becoming a trend. I think I used to have harder time to convince people, but I guess I no longer need to convince you really hard, because we're already seeing a lot of works that at least in the NLP field, that very successfully does large-scale representation learning, like BERT and GPT series of works. And we're starting to see similar works in vision. I think Google Brain's European department had Big Transfer, BIT, and Vision Transformer, with both of which are essentially doing large-scale representation learning for computer vision. And the reason that this is fully attentional modeling is very suitable for representation learning. One of the main reasons, which I already said, is that it kind of creates higher capacity network with the same amount of parameters. And when we are doing large scale representation learning, we really need very huge networks, and this is a very important advantage. Another advantage is that fully attentional models seem to learn faster than ConvNets. I will talk more about these in the final discussion part of this section. The final reason why we were pretty confident that this was going to work was that there was a work in, I think, I can't remember the year, maybe, I think it's probably iClear 2019, that shows that attention has the ability to simulate convolution. And they gave both a theoretical proof that for any given convnet, you can construct an attention network that does the exact same transformation. But they also had an empirical demonstration, which they kind of have a toy network. I think it was on SAFAR, showing that if you actually let an attention build a small fully attentional network and let it learn on a vision task, it will learn to simulate convolution where it should, basically means in the early layers. So with the 3 points of motivation, we started to dive into how to make a fully attentional model, how to make a fully attentional vision network. And the goal is essentially that we would replace all the 3x3 or 5x5 or n-by-n convolutions by attention modules. We would leave 1x1 convs there because 1x1 convolution is not really convolution. It's basically just a linear layer, and it's not. It's serving different purposes as these spatial modules, and it's not suitable for us to replace them too. And so that, for example, we have a bottleneck block here. We would replace the 3x3 conv in the middle, and we'll have a tension bottleneck block. And then if we build if we build a ResNet with a tension bottleneck block, we would have an attention ResNet. And the starting point for the effort was the efficient attention module, because this is actually point 0 of our motivation, was that I had the assumption that the reason why attention had taken off in language but not in vision was that attention was too expensive on computer vision, that we couldn't afford to build a full attentional network. And now that we have an efficient, linearly complex attention module, we would have a starting point to build such a network. But this thing has a very big disadvantage when used as the backbone for vision networks, which is that it lacks spatial information. And because what you can see from this diagram is that all of these are matrices. They are like rank 2 tensors. It has one spatial dimension and a channel dimension. But when you're doing computer vision, you usually have rank 3 tensors, which have a height dimension, a width dimension, and a channel dimension. So in order to fit an image or image feature map into this module, you are essentially just flattening the image and destroying all the spatial structural information that's embedded in the image, which are very important to make a vision network work. Because I'm not sure how familiar you are with Google products. If you are, I have a joke about this. So basically, if you are not able to see the spatial structure, but only able to see the color of an image as basically a bag of pixels, then all Google products now basically have the same logo, like exactly the same, because they're all just basically the 4 colors arranged in different orders. Yeah, but I guess it's not very difficult to understand that spatial structure is critical to understand image, because if you just randomly scramble an image and completely destroy its spatial information, it will be very hard to recognize even very, very simple things I don't know, like some traffic signs, for example. Yeah, so in order, when efficient attention was an auxiliary module, that wasn't a problem because you can rely on ConvNets, you can rely on convolutional modules, which are very good at extracting spatial information from the images. And efficient attention needed only to focus on the parts that convolution couldn't do very efficiently, like establishing long-range connections. So that it wasn't a problem for it. But now if we want to essentially eliminate convolution and make this the backup module, it has to have the ability to model spatial information. And there's very established ways to do this. From the NLP literature, we have position encoding, which essentially, when we are matching Q and K, we don't just simply multiply them to each other. We add something to K. We add something to KJ. We add a PJ to KJ, and then multiply the sum to QQ to QI when we're computing this IJ similarity. And the PJ would be a vector that depends only on the position of pixel J. So you can imagine that we basically have one vector representing each spatial location on the image, and there are different ways to do it. You can actually just have one vector for each pixel, or you can assemble them from its you can have a horizontal embedding and a vertical embedding, concatenate them to form an XY embedding, or you can for the actual embedding you can just randomly initialize some embeddings and train them together with a network, or there are some handwritten embeddings, for example sinusoidal embeddings. So essentially this is a very established field method, and it works very well in NLP. But in vision, this doesn't work as nicely because the position information here is absolute. So PJ, for example, if J is 2, 5, it basically just looks at J and see that it's 2, 5 and retrieves the vector that represents pixel 2, 5. That's not very informative because a very important property of images of vision system is that it's called translational equivariance, which means that, for example, if my hand is here, it's my hand. If I move it somehow to here, it's still my hand. So the absolute location of an image on an image is not as informative as the relative information between different pixels. So just because we have like some pink pixels here and some blue pixel here and some pink pixel here, and this pattern forms a hand. If it's arranging other ways, it might be my face instead. But if you ask a network to learn these relations from absolute pixel coordinates, it will be very, very hard because you're essentially telling it this pink pixel is at row 280 and column 350, instead of telling it it's besides some other pink pixels which are besides some bad pixels. It will be very inefficient. It will be much more efficient if we can instead inform the network of relative positions between pixels. So that will bring us to relative position embedding, which is still very simple. So instead of having PJ, which only depends on J, we have Rj minus I, which does not depend on J itself, but depends on the displacement from I to J. So that when pixel 2, 5 is looking at pixel 1, 4, it is looking at it the same way. It is having the same embedding as pixel 3, 6 is looking at 2, 5. And this essentially just solves the problem I just mentioned. Like the inefficiency of recovering translational equivariance from absolute pixel coordinates. But this also comes with its own problem. The problem is that this term does not depend only on J. It also depends on I, so that you can no longer arrange this into a matrix. So you cannot just have a K plus R matrix. Back here, you can have a K plus P matrix. Here, you cannot have a K plus R matrix. So you have to have this direct multiplication between Q and K. And this just breaks the multiplication structure, matrix multiplication structure, and breaks the efficient attention method. Therefore, we eventually decided to introduce a second variant of efficient attention, which is called axial attention. It's also fairly simple. It basically factorizes one attention layer into two attention layers. And the first one, within the first layer, each pixel will only attend within its own row. And in the second layer, each pixel will attend only within its column. Because in this layer, every pixel has already seen its own row. So you can see through your own column every pixel. So in this two-step indirect manner, you still get to see the entire input in this one single module. The complexity is slightly higher than efficient attention. It's instead of linear, it's O of n log n. Of n square root n. And also the globality is no longer direct. It's a factorized indirect globality. Therefore, we decide to combine this with efficient attention and form our GSA module, which has two branches. One branch just uses efficient attention and cares only about the content. So this branch, as before, does not respect the spatial structure of an image at all. The second branch is an axial attention branch, and this branch specializes at modeling position-dependent interactions, so that this branch doesn't even take in the keys. It directly uses the relative position embeddings as keys, and have this match that with the queries and aggregate values and get the eventual output. And the final output of this module is simply the sum of the output of both branches. So with this, we now have a module that is both efficient and fully attentional, and also knows how to model spatial information. And therefore, we can finally achieve what we wanted to achieve in the first place, which is to replace all 3x3 convs in the bottleneck block. So, and use this GSA bottleneck block to replace all bottleneck blocks and build, for example, we can build GSA less than 50. We can also replace things in other types of networks. And the empirical experiments are pretty encouraging. We can see that no matter we control the number of parameters or the amount of computation it takes or the actual runtime, we can see that GSA-Net's the trade-off curve of GSA-Net is quite a bit above traditional CNS, and this is in all these experiments we're using ResNets as the overall architecture. Although the runtime advantage is much more minimal compared to flops and parameters. Yeah, so this is the discussion part of this section. I'd like to go back and revisit some interesting points that I have brought up before. So the first one is that attentional networks exhibit higher capacity. It could be seen from a few different facts. Firstly, obviously the performance is higher, so larger networks usually gets higher performance. So that's one indication that attention networks seem to have higher capacity. But a more decisive evidence is that these experiments are done on ImageNet, on the entire typical ImageNet data set. And on ImageNet data set, our GSA-Nets are obviously significantly better than ResNet. And we did a set of experiments which tried to train these networks on subsets of ImageNets. We tried from, I think, 30% to 90% of the ImageNet data. And the result was very interesting that as we have fewer and fewer data points feeding into the network, the performance gap starts to shrink between GSA-Net and ResNet. And at 50% ResNet, the two networks essentially starts to have the same performance. And below 50, when we have 40 and 30% of ImageNet data, I think we also did 20%. Yeah. GSA-Net start to underperform ResNet. This looks like a very the very typical behavior of a higher capacity network. So it has better results, but also it needs more data. When you have not sufficient data, it overfits more easily, and it overfits more easily and gets instead worse performance. And a second interesting point is that attention networks learn faster. So again, here you can probably see like a few percentage point difference between GSA-Nets and conv-nets, which is the performance difference we get at the end of training. But in the middle of training, when we are like 30% finished or 50% finished, the performance gap was much wider, which essentially says that attentional networks learn much faster than their convolutional counterparts. And this does not seem very useful in today's context, because you should train networks until they converge. And what matters is the performance after convergence. But when we start to move into the large scale pre-training paradigm, this probably actually starts to become much more meaningful, because I guess you probably have heard about like the gigantic scale of GPT-3. It costs $12 million to do just a single training run. And similar things are starting to happen in the vision field. We are doing these kinds of super large scale pre-training. Sometimes you just can't afford to train until convergence. You instead have to find an optimal point where your network is performing reasonably well, and further training, you know that it will bring better performance, but the return does not justify spending more resources on this model. In that context, networks that learn faster are much more valuable than networks that learn more slowly. And so that both of these points point to one of the motivation points that's discussed before, that attentional networks have much better synergy with the oncoming large-scale pre-training paradigm in comparison to the current way of doing deep learning. But the network also, our GSA-Net also has some pretty important drawbacks. And the biggest one is that the runtime comparison we showed was a single example inference time. If we do batched inference, it is actually much slower than conv-net. I think it's about 4 times slower on TPUs and maybe 2 to 3 times slower on GPUs, which is quite significant. And because batched inference is a much more common use case than single example inference, this actually renders the network not so practical in its current form. And I think later, as more popular works like Vision Transformer demonstrated, there is an alternative path to do visual self-attention, and their method does not suffer from this problem and has already seen much wider adoption than this paradigm. Yeah, so this is basically it for my presentation today. Thank you so much for attending. And yeah, I think this is one of the biggest presentation I've ever given, measured by the number of audience. So I'm very excited and thankful. And if any questions that you haven't asked during my presentation, it's time to ask now.
Can I ask a question, please?
Yeah, sure.
Okay, so your actual attention is the most relevant for problems like segmentation problems, like depth estimation problems, where you actually need like output be very similar, is dependent on the lattice that is broken by like attention mechanism. So it is interesting to me if there are comparison results between fully attentional network for this task versus like units and so on. Can you just, do you really know that attention-based networks for these type of problems are working better than SPI-Net or UNet?
Yeah. So, yeah, it is true that attention is more important on pixel level or instance level tasks than image level tasks. So we see much more benefit when we apply it on segmentation, detection, stereo vision, tracking, these kind of things, than image classification, scene classification, things like that. But we also have experiments. For example, this set of experiment is on ImageNet. And we have shown that it also brings benefits on classification tasks. And I think efficient attention, when used as an auxiliary module, also brought benefit to image classification, just not as significant. To answer, I think the second part of the question is like, do I know that attention models work better than UNets and SPI-Nets on segmentation type of tasks? Is that correct?
Yeah, exactly. And moreover, because the capacity of the network is larger for attention models, you also need more data for generalization. So it's interesting to me what is the state of the art of attention models for visual tasks with like segmentation, like depth estimation versus all the methods like UNet, SPI-Net, and so on.
Yeah, I see. I think if you use attention as an auxiliary module, I think it's fairly common now to add attention modules into ConvNets when you're dealing with segmentation and detection problems. So I think that's already inside the state of the art. I think it has been like that for a while. For fully attentional models, I think it's still a fairly new field, and people are trying to find the best way to adapt vision transformer type models to segmentation and detection. I think on detection, we're already seeing pretty good results. On segmentation, I don't know of any, but as I said, I've been in vacation mode for a while. I haven't been tracking the literature very closely, so maybe it's just that I don't know. So I'm not too sure about the answer.
And if you speak about relative positional encodings for problems like with segmentation propagation, so what will be a relative positional encoding? Is it between positional encoding between time of the frames, like the first frame, the second, the third one, or it's between actually different pixels in pixels taken in different times?
Now position encoding is very general. You can use it for any coordinate system, but the one I talked about in my presentation were dealing with the pixel space. So it's like pixel space XY.
Yeah, I understand. It's exactly my question. So if you do it within the image, so relative encoding, positional encoding is like straightforward. But if you want to solve a problem of segmentation propagation, like in the middle of your lecture, you actually have pixels in, let's say, in the first image, and you have pixels in the second image. And for I think that you want to compare each pixel in the first image with all pixels in the second image. But now you are not within the image. Your pixels are moving. So how do you do that in this case? Okay, maybe it's worth to take offline. Because you need relative positional encoding. Within the image is straightforward. But if you have like images, the stream of the images, and like images are like objects are moving in the image, so it's very difficult like to make this relative positional encoding in video streams.
I would say when you're dealing with a video, you can obviously still use 2D relative position encoding within each frame, and it's essentially it essentially boils it down to trial and error on what's the best way to deal with the temporal dimension. Because I think in the video domain, it is very common to do different things to spatial dimensions and the temporal dimension. So I haven't tried. I don't know what's the best way, but there are many ways to do it. You can treat it the same as a spatial dimension, have a 3D relative position encoding, or you can use just simple. You can have an additional 1D encoding for the temporal dimension that can be relative or absolute, or you can even just not have. You can even just not have any position encoding for the temporal dimension, which I guess worked in the global context module.
Okay, thank you.
Yeah, I remember there was a like raised hand, but I couldn't remember who it was. I think it's your turn now. If you are still here.
Again, what?
Sorry?
Could you repeat? I'm not sure I understood.
Oh, I was saying that I remember I saw a raised hand in this Zoom meeting. Yeah, but I couldn't remember who it was, and I was asking if they are still here, it's their turn.
In the meantime, I will say we actually had more viewers also on the YouTube, so like about 5 to 7 people were there as well. And this is nighttime for parts of the world, and I know some people are watching the recordings because they usually can't join the sessions. So expect more viewers coming that direction as well after the recording is published.
Cool.
Yeah.
And can I ask another question? So
sure.
Yeah, so is there some, like, there is still a lot of parameters in attentional models as well. So regarding the local minimums, are they more prone to converge to local minimums, and this is why they converge faster, or it's not the case?
I think to the first part, attentional models have way fewer parameters than convolutional networks. You can see if you control for the same performance, it has like 1/3 of parameters. And part of the reason is that the connection between pixels are dynamically generated. So you don't need to hard code the connection strength everywhere. And also the many parts in this network is parameterless. So this matrix multiplication is parameterless. This one is also parameterless. We only have parameters when we generate Q, K, and V, and all three of them are generated using linear layers, so it's very parameter efficient. Yeah, and then I actually colored this diagram by making parameterless modules green and parameter modules blue. So it's very obvious. And the same goes for efficient attention. Yeah, and to the second part, I think it's a much more difficult question. I haven't tried. I don't know if it's more prone or less prone to local minimum.
Does it mean that we converge faster because there are less parameters?
So sorry?
So I just want to understand why we converge faster, why attentional models converge faster than like convolutional networks. Is there any explanation, like intuitive?
Yeah, it's a very interesting phenomena, and I mean, and I have not made up an explanation that is very convincing to myself. Sorry about that.
But isn't it related just to the less number of parameters, as you said?
Sorry?
So, but you said that there are less parameters in attentional models. Isn't it
Yes.
related to the fact that there are less parameters and like the space of optimizational space is smaller, and this is why it converges faster?
Yeah, I guess it could be for that reason.
And if you just train the same models, but starting from different conditions, will it converge to different attentional mask, or there is some stability? It's just, I'm just curious. It's not that I want because I didn't work with these models and I would like to work with these models. I just want to know what to predict. So let's say I have the same model, but I initialize differently all the initial weights. So will I just converge to the same attentional mask, or it will be something different at all? So how stable are these attentional masks?
I think it's fairly stable, because if you look at the visualization, where is that? If you look at the visualization, I actually didn't talk about this, yeah. So for example, this channel, I think you can probably tell that it's segmenting out it's contrasting foreground versus background. This model is trying to find the core part of objects, and this model and this channel is looking at object boundaries. And what we saw in a lot of the channels is that you can kind of attach a semantic meaning to a lot of the channels. So it's I guess it means that through training, the attention module would learn to discover these concepts that are helpful for later processing. And if that is the case, I would expect that the set of attention map semantics to be relatively stable. Of course, like the channel order would shift randomly based on random initialization.
And also, you thought that, let's say, any convolutional network can be, you can find like counterpart of it, like something similar as an attention network. So my question is, let's say I have some attention network. Can I convert it to be like convolutional? Can I explain it as convolutional or vice versa? So can I just transfer one of the, so let's say I have convolutional network, can I transfer it to attentional? Let's say I have attentional, can I transfer it to convolutional to have more explanations, something like this one. So to have some explanatory mechanism. So maybe I'm wrong, but it's like So I just want to find a bridge between two worlds, the world of convolutional networks and the world of attentional networks.
Are you asking, can we convert any ConvNet to an attentional network and convert any attentional network into a ConvNet?
Yeah, or approximation of it, something like this one, yes.
Yeah, I think for the forward direction, where is that? Forward direction, essentially this paper, I think the full title of this paper is called On the Relationship Between Self-Attention and CNNs, if I remember correctly. Yeah, but anyways, the link is in my slides. So this paper has proven that given any ConvNet, you can construct an attentional network that does the exact same transformation for any data up to the accuracy of floating point numbers. And but backwards doesn't work because, for example, the first layer of an attentional network there could be a pixel that is seeing far away. It's seeing like 80 pixels away. That would not be, you would not be able to reproduce that in a ConvNet. So this is basically a one-way relation, and I guess you can say that the set of all attentional networks is a superset of the set of all CNNs.
Yeah, but it depends on the receptive field. So if receptive field is very large, then it's I can reach any with convolution networks. I can also just have very wide receptive field and to reach any pixel in the image. So it's like
yeah, but that's kind of yeah, I guess so. But that's kind of already making the ConvNet looking very much like a fully connected network.
Yeah, but in a way, your actual trick is also just trying to reduce receptive field, because you have this like if you have like exponent, then it means that you have two matrices. One of them is like also reduces receptive field in a way.
I think that there's another point, which is that attentional networks are dynamic. So so ConvNets like is fixed. So it is very easy to find two examples that stimulates different connection patterns in an attention network, and you would not be able to simulate that with a CNN.
Okay, I see. It's very interesting. Thank you very much.
Yeah, I mean, like CNNs are. I think CNNs is CNNs are also able to simulate any possible functions. So if you have a large enough CNN, like try to use different channels to represent different attention, different attention patterns, I guess. If you have enough channels, that would eventually work. But that type of network doesn't really look like a CNN anymore.
Okay, see, I understand. Okay, thank you very much.
I think we're past the time.
I have a question.
Go ahead. Go ahead.
Okay. So you said that the convergence of attention network is faster, right? So does it mean that it would work better for tasks where you have a smaller data set, where you want to converge faster because you don't have enough data for a segmentation, for example?
It actually works worse. So it learns faster, but when but you have to have a variety of data. If you have fewer data points, actually it works worse than CNNs.
Okay, thank you.
Yeah, that's actually why we had the set of experiments like trying 90 through 20% image sets, because like we saw it learn faster, and we were thinking that maybe it's better at low data regime, but it's actually not, unfortunately.
And the last question, I guess that there is a lot of models that, which are combinations of like U-Net and attention. Like attention blocks, because when you actually need to be near, like your output should be very correlated with input, where you have edges and all this information that is very, very high resolution. So you can actually like work with UNet, but at some, like when you go to some downsampled resolution layer, from which layer you can start using attention mechanism. And then having this ResNet blocks back. This is what I predict, but it's interesting to me if there are works like this one that are like hybrid combinations between hybrid architectural like combinations of units and attention blocks.
Before we had efficient attention, when we only had traditional dot product attention, the way to use attention with UNet was to insert it into the low resolution part, like in the low resolution bottleneck. Because that was the only place that it would fit. It would fit in memory. But after we have efficient attention, we will be able to insert it at high resolution parts, and we usually tend to insert it at the end of the network because it's more semantically rich. And I think we haven't actually tested UNet, but I think feature pyramid network is essentially a different implementation of UNet. And if our knowledge does transfer, then inserting efficient attention in the higher resolution part is more helpful or more impactful than inserting it at lower resolution parts. But that couldn't have been done when we didn't have efficient attention.
And the last question. So what do you think will be like new questions or new directions in attentional networks? So what people should do in this direction? So what do you expect to see? What will be the kind of research that people will do with attentional networks?
Yeah, so in the short term, I think because fully attentional visual networks is still a very new field, there are many obvious things to do, like making it work on a variety of vision tasks, because people have been mainly focusing on mostly classification detection at this point. But I think it has been trending for a while, and it seems that it's better than traditional CNN. So I guess it's worth it to try to bring it to every other field and see if it works here and there. And in the longer term, I think I'm kind of seeing and kind of believing in the transition towards large scale pre-training. I think the BERT and GPT style pre-training will also come to computer vision eventually, and that would be a much larger paradigm shift. And as I said, I think attention networks are more suited for this paradigm. And but that's a very big change, and I guess I'm not very confident to say what will happen after that actually comes.
So you mean this paper that is called DINA, I think, yes, in this respect. There is the paper that is called DINA, D-I-N-O, and this is what they actually, one of the claims of the paper is that for attentional networks, pre-training is more worth than even for convolutional networks. There is a paper already like this one. It's called DINA. I don't remember how it is translate.
I see. Yeah, thank you for sharing that. Probably you can message me the full paper name or what you can remember, and I will try to find it.
No problem. Thank you very much. It's interesting.
Yeah. Any more questions from anyone else? Oh, by the way, I'm sorry that when I'm doing QA, I'm looking this way because in order to see both you guys and the and the slides, I'm attaching my laptop to the TV, so it's a weird angle.
That's okay. Everybody, last chance for questions. In the meantime, I'll be wrapping up. If you have a question, just join in. Joan, thank you for this talk today. Was tough a bit for me to follow. I think this topic is very mathematically it's challenging. So good job for making it as easier to explain as possible. Extremely interesting stuff. Thanks everybody for joining.
Thank you so much for organizing this and waiting so long after this winding journey to make it actually happen.
When did we start talking? Was it April? Something?
Yeah, probably
then?
April or March.
So for anybody who's watching
Google back then, and so we even switched from my Google email to my personal email.
Yeah. Anybody who's watching this really, so you understand how tough it is to organize these events. And I'm always asking if anybody knows of anybody good to reference or to help out to bring good talks. Please let me know. It's not an easy job, as you can see now. Still, thanks everybody for joining. Thanks for your engagement and for asking the questions and all the engagement also in the community. From my end, this is it. So I could say bye to all. We'll see you next time. You know what? Last thing before I forget, I'll add here again the links where you can find us. If anybody wants to join one of the community places or the newsletter, it's in your chat now. Take a copy of it because in 1 minute this chat is gone. Thanks all. And again, until the next time. Bye for now.
Yeah. Thank you everyone for attending my presentation.
Thank you very much. Great talk.
Thank you very much. Really good talk.
Bye-bye.
Thank you.